Hi everyone, I'm Vidisha Hosambre, and this is my video lab report for Lab 2, Motion of a Falling Object. The objective of this lab was to observe and analyze an object in motion that has a non-zero velocity and therefore a non-zero net force, according to Newton's second law. In this lab, a foam cup was dropped from a height of 4 feet and its motion was observed on tracker and was depicted as a curve increasing in the negative y direction. Computational models with gravitational force and with drag force were created in VIDLE to see which best predicts the motion of the object as it reached terminal velocity. The two main physics principles discussed in this lab are Newton's first and second laws of motion. Newton's first law states that an object in a state of uniform motion tends to remain in that state of motion unless external forces are applied to it. In this case, the foam cup does not stay in uniform motion, and we can conclude that this is due to the external forces of the Earth's gravitational pull and the drag force due to the air acting on the cup. Now, Newton's second law tells us that force equals mass times acceleration, from which we can derive the equation V final equals V initial plus F net divided by the object's mass multiplied by the change in time. We know that the change in velocity is not constant, and so F net is a non-zero value as well. Since F net is defined as the vector sum of all the significant forces in the surroundings, we know that there are interactions affecting the motion of the system, which in this case are the weight force and the drag force. We must take these interactions into account in order to successfully model the cup's motion. Now let's take a look at the video footage in Tracker. The system is the cup and the surroundings are everything around it. The motion of the 5.5 gram foam cup was plotted on an XY plane with the center of mass of the cup at the origin. The width of the cup, 8.89 centimeters or 0.0089 meters, was used as a length scale for calibration. The axes were slightly tilted to make sure that the object travels along the negative y-axis. The motion of the cup was captured in time intervals of 0.042 seconds. To the right is a position versus time graph for this motion, and we see a curve indicating that velocity is not constant and that acceleration is present. As time goes on, however, the data becomes more linear, indicating a more constant velocity. At the very end of the motion, the graph shows a curve ending a little farther than following the trend in the data, and this was due to the cup bouncing off the ground as soon as it hit the floor and ending up a little to the left of the y-axis. The following slide shows the initial position of the cup, the initial velocity of the cup, which was 0 since the cup starts at rest, and the start and end time of the motion. This data, along with the mass of the ball and the gravitational constant, was then inserted into the sample code that was provided. The time step was set to the low value of 0.001 to ensure the data is as accurate as possible. The velocity and position of the object were set to reflect Newton's second law, and F net is set to equal the weight force. When we run this model, we see that this model greatly overpredicts the motion of the cup. This is because, in addition to the weight force, there is another force acting on the cup, the drag force. The drag force can be calculated using the following equation, where b is a proportionality constant and is multiplied by the magnitude of the object's velocity squared. This can be represented in the code as follows. Now F net is set to be the sum of the weight and drag force. The value of the proportionality constant b can be determined by trying different values until the model's final position mirrors that of the observation. Unlike the model with just the weight force, this model more accurately correlates to the motion of the cup. When taking drag force into account, the model is able to more correctly predict the position and motion of the cup. The slight discrepancies in the experimental and model data could be due to human error while tracking the motion of the cup on Tracker. Now let's take a look at the questions. What does it mean? When examining the velocity versus time graphs for only weight force and for weight force and drag force, we see that the second model does a better job than the first model of hinting at a terminal velocity, as we see the curve begin to straighten out. If an object with greater surface area and smaller density had been used, then we would have seen this graph curve downwards in the beginning due to the effect of gravity and then straighten out till there is no change in velocity, and that would be when terminal velocity has been reached. Since my foam cup was more on the heavier side, if I had dropped it from a higher altitude, then we would have more likely been able to observe terminal velocity. The second question, what if, asks how initially throwing the object downward would affect terminal velocity. If initial velocity is set to 12 meters per second, the model shows us how the drag force is now greater than the force of gravity. The object initially decelerates and then continues downward at a constant velocity, which is indicated by the linear part of this graph. Regardless of what we set our initial velocity to be, the terminal velocity will still be reached and at approximately the same time, because this value is dependent on the mass and surface area of the object and the density of the medium it is falling through rather than initial velocity.